Okay, let's dive right into this explainer and honestly, completely shatter your common sense understanding of how space and time actually work. If you've ever felt like time is just this steady ticking clock in the background of the universe, well, you're about to see that reality is way more flexible, it's incredibly strange, and it is entirely dependent on how fast you're moving. Today, we're exploring Chapter 37, Relativity, unlocking the absolute game-changing secrets Albert Einstein dropped on the world back in 1905.
Here is our flight plan for dismantling classical physics step by step. We've got the postulates, simultaneity, warping, transformations, velocity and light, and finally, momentum and energy.
All right, part one, the postulates, the absolute rules of the universe.
So before 1905, physics was pretty much governed by our everyday, slow-moving world. But the core mystery we're exploring today is this: what actually happens to reality when you push the absolute limits of speed? Because, as we're going to see, the universe has a very strict speed limit, and protecting that limit requires reality itself to literally bend.
299,792,458 meters per second. We usually just represent this with the letter c. Now, this isn't just how fast light travels in a vacuum, it is the ultimate cosmic speed limit. Zero exceptions. No mass, no energy, and absolutely no information can ever exceed this exact number. So here's the crucial point. Einstein gave us two deceivingly simple postulates that completely break our classical, slow-moving experience of reality. The first basically tells us that if you're in an inertial reference frame, which just means you're moving at a constant speed, you're not accelerating, all the laws of physics work exactly the same for you as for anyone else. There's no preferred stationary spot in the universe, right? Okay, but the second postulate is the real mind-bender. It says that no matter how fast you are moving towards or away from a light source, you will always measure the speed of that light as exactly c. It never changes.
Which brings us to part two, simultaneity, breaking now.
Okay, because the speed of light is absolutely constant, our whole concept of two things happening at the same time basically has to be thrown out the window. Let's imagine Sam is standing totally still on a train platform, and Sally is zooming past him in a spaceship. Two light flashes go off, one red, one blue, at exactly equal distances from Sam. The light reaches Sam at the exact same moment. So to Sam, these events are perfectly simultaneous. But Sally? She's moving toward the red flash and away from the blue one. Because light always travels at that constant speed c, the light from the red flash is going to reach her before the blue one. To Sally, the red event definitely happened first. And here's the kicker, you guys. Neither of them is wrong. Both of their realities are mathematically correct. Simultaneity is completely relative.
Moving right along to part three, time and length warping, the mechanics of reality.
To protect that unbreakable speed limit of light we just talked about, space and time themselves must bend. They have to warp. First, we need to define proper time. This is simply the time measured by an observer who's at rest relative to the events happening, using just a single clock at one location. For anyone else moving past that clock, time will actually stretch out. It dilates. And to show why this actually matters in real life, if engineers didn't account for these relativistic time changes, the GPS in your phone would become completely useless in less than a day. The satellites are moving fast relative to us down here, so time literally ticks differently for them.
Similarly, we have proper length. That's the measurement you get when you are completely at rest relative to the object you're measuring. Like if you're standing next to a parked spaceship, you can easily measure its proper length, no problem. But if that exact same ship flies past you at high speed, you'd have to measure its front and back simultaneously. And since we just learned that simultaneity is relative, your measurement is going to change.
Now, what's really fascinating here is the Lorentz factor, usually represented by the Greek letter gamma. You can think of it as the universe's scaling variable that kicks in the faster you go. At normal everyday speeds, gamma is basically just 1. We don't notice any relativistic weirdness when we're walking around or driving a car. But as your speed approaches the speed of light, this factor just rockets upward toward infinity. It is the absolute mathematical heart of both time dilation and length contraction.
So what this brilliantly illustrates is that a moving observer will always measure a stretched out, dilated time and a squeezed, contracted length. Look at it this way. If you multiply proper time by our Lorentz factor, you get a larger number, which is time dilation. Moving clocks run slow. But if you divide proper length by the Lorentz factor, you get a smaller number, which is length contraction. Moving objects literally shrink along their direction of motion. It's wild, but space and time are physically adjusting themselves so that the speed of light never, ever changes.
Part 4. The Lorentz transformation, the hidden machinery.
Okay, so let's look under the hood. How do we precisely translate an event from Sam's stationary reality to Sally's moving reality? Well, before Einstein, physicists used these classical Galilean equations that just assume time ticked at the exact same rate for everybody. The Lorentz equations correct this for high speeds. By taking the space and time coordinates from one frame and factoring in the relative velocity, we can calculate the exact coordinates in the moving frame. And what this reveals is incredibly profound. Space and time are permanently entangled. The equation for calculating Sally's time isn't just based on Sam's time, it's also based on Sam's space coordinates. A spatial separation for one observer literally creates a time difference for another. They are completely linked.
Part 5. Velocity and light shifts. Chasing the wave.
Now we apply this warping to objects in motion. Because of relativity, you can't just add two velocities together simply anymore. Like in classical physics, if you're on a train moving 50 miles an hour and you throw a baseball forward at 50 miles an hour, the ball is moving 100 miles an hour relative to the ground, right? Makes perfect sense. But what if the train is moving at half the speed of light and you fire a laser forward? Does the light move at 1.5 times the speed of light? No way. The universe's math, specifically the relativistic velocity transformation, prevents any combined speed from breaking c. The denominator in this equation ensures the math always scales perfectly below the ultimate speed limit.
And you know how the pitch of an ambulance siren shifts as it drives past you? Well, light waves actually shift depending on motion too. But since light speed cannot change, its wavelength changes instead. When a light source races away from us, the waves stretch out, shifting toward the red end of the spectrum. When it races toward us, the waves compress, shifting blue. This relativistic Doppler effect is an absolute game changer. It's exactly how astronomers know for a fact that distant galaxies are expanding away from us.
And finally, Part 6, Momentum and Energy, the grand finale. We have arrived at the climax of our observer's journey, looking at the ultimate cosmic consequences of all this. As an object with mass accelerates closer to the speed of light, our old friend the Lorentz factor strikes again. The object's momentum and kinetic energy don't just increase steadily, they skyrocket exponentially. As the speed approaches c, the energy required to accelerate the object literally approaches infinity. And since there isn't infinite energy in the universe, no particle with mass can ever actually reach the speed of light. It acts as an absolute, unbreakable physical barrier. Which brings us to arguably the most famous equation in history, E equals mc squared. Einstein elegantly stated that the total energy of an object is equal to its mass times the speed of light squared. This completely revolutionized physics because it proved that mass and energy aren't two different things. They are ultimately the exact same thing. Mass is basically just super concentrated energy.
To put this incredible concentration of energy into perspective, let's look at some equivalents. A tiny electron or a proton has a pretty minuscule amount of energy, but look at a standard everyday object. The mass inside a single US penny, which is just over 3 grams, contains the energy equivalent of 78 gigawatt-hours. I mean, if you could fully convert the mass of that penny into pure energy, it would be enough to power a major city for a considerable amount of time. That is the sheer, unbelievable power locked inside the fabric of space-time.
So, we've seen how pushing the speed limit of the universe forces time to stretch, space to shrink, and transforms mass into boundless energy. I want to leave you with this really provocative thought. In a universe governed by relativity, where your physical now is completely different from a moving observer's now, whose perspective of reality can we actually call the truth?